Welcome to our next video here. Today we're going to talk about how to do a change of basis using linear algebra and matrices. First off, let's start off with this guy. So we're going to take S prime, and he's going to be the vector 1, 1, and negative 2, 1. Is he a basis for R2? I'll give you a second to think about that and explain how you got your answer. The answer is yes, he is a basis for R2 because we have two linearly independent, because there's only two vectors, you only have to check if they're scalar multiples of each other, which they are not. We have two linearly independent vectors in a two-dimensional space, and so we know that that is a basis. So our favorite basis for R2 is I and J, okay? And these are two vectors, and why they're our favorites is because they are orthonormal, meaning they're each orthogonal to each other, and they're normal, they're length 1. And I'll do those guys in red. And they basically create our regular square coordinate system, square because each step in the horizontal direction is the exact same length as a step in the other vertical direction. Okay. Well, we got done saying that 1, 1 and negative 2, 1, they do form a basis. Therefore, we can create a system with them. So if this is vector 1 and this is vector 2, okay, they create a system. And you'll notice that if I inner product them, I don't get 0. So they are not orthogonal and they're not each length 1. So they're neither orthogonal nor normal. So they set up a non-square coordinate system. So what we want to do now is be able to switch between coordinate systems. So I've recopied these guys down here. And so here's our regular standard IJ basis. Okay. And then here's vector V1 and V2. But I've superimposed the IJ basis here on this one. So I'll even throw those in. So there's I and there's J. Okay. So if we wanted to plot the point 4, 1 on the IJ system, what that literally means is 4 of the first vector plus 1 of the second vector. And we sometimes note that as 4I plus 1J. So we do 1, 2, 3, 4 of the I vector plus 1 of the J vector. So the point 4, 1 is here, okay? If you wanted to, we could connect him to the origin and make a vector out of him. Now, how could I locate that same position, but in the V1, V2 system? Well, because I superimposed the grids, I'm going to go 1, 2, 3, 4, and then up 1 if we were the IJ. And so to get here, but I only get to use the blue vectors. Fortunately, I've superimposed the IJ grid, or sorry, the V1, V2 grid on here. And so to get there, I would go like this. So that would be the easiest way to get to that location. So that would be a vector V1 plus another vector V1 and an opposite of vector V2. So it would be 2 V1s minus V2. Okay. All right. So we're going to take and, I'm going to show you something else that's pretty spiffy here. Let me show you an applet that I found. It's on the top of your paper. So you'll load it up here and then start clicking. So we've got some points there. Okay, and so we take our standard basis vectors. We can show our standard axes and our standard grid and how to get there. So to get to the point 4, 1 is going to take 4 of the first I vector plus 1 of the J vector. They're calling them E1 and E2, elementary 1 and elementary 2, but that's okay. Same difference. Okay, so what if we create a new set of basis vectors? And I used 1, 1 and negative 2, 1. Let's move this guy over here. Okay. And so how would I use those to get to my location of 4, 1? Well, let's go ahead and show both grids. And so to get there, we do 2 of the orange vector, which is the first vector I've called V1, minus 1 of the green vectors, V2. And so that would get us to the exact same location. Okay. All right, let's go back to our paper to see what we've got going on. Oops, there we go. All right, so what I'm going to do here is take and express the W vector as a linear combination of the 1, 1 and negative 2, 1 vectors. So to do that, remember that we're doing W is equal to some scalar multiple of vector 1 plus some scalar multiple of vector 2. I'll use K1 and K2. So literally what we've got going on here is 4, 1 is equal to K1 times 1, 1 plus K2 times negative 2, 1. Okay. And if we do the algebra on the right-hand side, we get K1 minus 2K2 and K1 plus K2. And if these are in fact equal, then we see that K1 minus 2K2 is equal to 4, so that the first components are equal. And if the second components are equal, then K1 plus K2 is equal to 1. Okay. And we could set this up as a system on our calculator. We could solve this using substitution. We might even do some basic elimination. But I'll just go ahead and RREF this matrix. And let's see what we get. So I just typed it into my A matrix here. Hopefully you can see that okay. And so if we, matrix math RREF matrix A, we'll see that when we solve that system, we get the identity on the left-hand side and we get 2, negative 1. So let's write that down here. Okay. All right. Next up, let's go ahead and talk about how we could find the coordinates of the I vector with respect to V1 and V2, and then the J vector with respect to V1 and V2. Well, we're going to be doing the exact same thing. We're going to be writing this I vector as a linear combination of V1 and V2, and the J vector is a linear combination of V1 and V2. So we'd have I is equal to K1 V1 plus K2 V2, and J is equal to M1 V1 plus M2 V2. All right. Now, since these are going to involve the exact same coefficient matrix, I'm going to try to be a little bit more judicious. And I'm going to augment first by the I vector, which is 1, 0. And since it's going to involve the same coefficient matrix, I'll augment again by the J vector to see if I can find out what my K1, K2, and M1 and M2 vectors are. So let's do that on our calculator. When I do that on the calculator now, I get that M1 is 1/3, and I'm sorry, K1 is 1/3, K2 is negative 1/3, M1 is 2/3, and M2 is positive 1/3. So the I vector is 1/3 vector 1 minus 1/3 vector 2, and the J vector would be 2/3 vector 1 plus 1/3 vector 2. And it probably wouldn't hurt just to see this in action right now. So let me go ahead and take and show that if we have the 1, 0 vector, if we do 1/3 times the V1 vector, which was 1, 1, minus 1/3 times the V2 vector, which was negative 2, 1. Let's look at the right-hand side. So we've got 1/3, 1/3. And I'll distribute the negative 1/3 through, so we're going to add plus 2/3 and negative 1/3. And 1/3 plus 2/3 is 1, and 1/3 minus 1/3 is 0, so it checks out. We'll pause right there and pick up in our next video.